As our friendly feline moves away from the patrol officers chasing her, the pitch of the sirens she hears lowers due to the Doppler effect, maybe to the point that the sound is outside the range of a cat's hearing. This could be used in her defense in a court of law. Do you see why everyone, including cats, should take a course in physics? So, what is the Doppler effect? Let's give a statement of it. The Doppler effect is a phenomenon where the wave frequency changes as the wave source moves relative to the observer. Examples of the Doppler effect? Okay, well, in the next slide, we'll take a look at a train as it approaches an observer, as it approaches a station, okay, and then leaves the station. Listen to the pitch, the frequency of the train whistle as it approaches and as it leaves. And you should notice a change in pitch as the wave source moves relative to the observer. This is an example of the Doppler effect. And as another example, something that I think everybody here can relate to, think of a time when you've been on the street and a police car or a fire engine has their siren blaring, okay, as they pass you. Think about the sound that you hear and what happens to that sound. We'll talk about this in the next slide. So you should notice, if you listen very carefully in the previous slide, that there are really two phenomena occurring simultaneously. As the siren approaches, the sound certainly gets louder. While the siren may create waves of constant energy, the sound wave intensity increases as the sound source gets closer to you, right? You've got the same amount of energy, okay, spread over a smaller area and volume. Remember, we said in part 2 of this video series that for spherical waves, there's an inverse relationship between wave amplitude and distance. So as you get closer to the source of the sound, okay, the amplitude increases. But this change in amplitude, this change in volume, has nothing to do with the Doppler effect. So it's important not to confuse the two. The Doppler effect has to do with the change in wave frequency. Did you notice that as the siren approaches you, there is a slight increase in frequency, an increase in pitch of the sound, okay, that you hear? And that when the siren passes you, there is a drop in frequency, a lowering in the pitch of the sound wave.
All right, so folks, what I'm going to do here is I'm going to illustrate the Doppler effect for you. And what I have here in this little box is a buzzer. okay, and I'm going to activate it here. You're going to hear it has a certain pitch. Okay, and right now that pitch should be fairly constant because, okay, if this behaves as a sound source, it is not moving towards or away from you. But what we're going to do is I'm going to set this in motion. I'm going to whirl it in a vertical circle above my head. So there's going to be times during that motion where this object, this buzzer, is actually moving towards you. That is where the source is moving towards the observer. And then there will be other times where the sound source is moving away from the observer. And what you should notice is a change in pitch. Okay, that change in pitch we said is characteristic of the frequency change that happens whenever a sound source moves towards or away from an observer. This is what we call the Doppler effect. So let me demonstrate this.
So what causes this change in wave frequency as the wave source moves relative to the observer? Let's take a look at a wavefront diagram to explain this frequency change. Notice in this diagram that as the wave source moves to the right, it is catching up to the waves that it has just emitted. Do you see how for the region in front of the wave source, the wavelength gets shortened? Okay, remember that there is an inverse relationship between wavelength and wave frequency, okay, for waves that travel at a constant speed. So for an observer in front of the wave source, this decrease in wavelength corresponds to an increase in wave frequency. Likewise, for the region behind the wave source, okay, where the source moves away from the observer, the wavelength gets bigger. Okay, according to our wavefront diagram. This would cause an increase in wavelength and corresponding decrease in frequency for an observer who sees the source moving away from them. So this simulation gives a nice illustration of the same phenomenon. In this case, our wave source is the tweeting from this bird, and the observer is the human ear you see. So notice that as the source moves towards the ear, the wavelength shortens, thus causing an increase in frequency, an increase in pitch heard by the ear. Likewise, when the bird moves away from the ear, the wave source moves away from the ear, okay, that causes an increase in the wavelength and therefore a decrease in pitch, okay, a decrease in the frequency. So in this slide, we will take a closer look at this observed frequency change when the source is moving either towards or away from the observer. So if you look in the diagram on your left, what I'm showing you here, okay, this is a spherical wave where we have a source, the source of the wave, let's say the sound wave, is at rest. Okay, and in this case, this sound source emits wave fronts that are all equally spaced because that source is not moving, and these spherical wave fronts form concentric spheres. Remember we said that the distance between any two wave fronts is a measure of the wavelength of the wave. And regardless of where the observer is here, wherever you measure the distance between the two wave fronts, whether you're measuring on this side, okay, on this side, okay, over here or over here, what we can say is that that distance between two wavefronts, in other words, the wavelength, always has the same value when the source is at rest. The wavelength is constant. Okay, and therefore the frequency, if the wave is traveling in an isotropic medium so that it travels at a constant speed, if the wavelength is constant regardless of where you're observing the sound wave, then the frequency will be constant as well. But now let's take a look at what happens in the picture on the right when the source of the wave is actually in motion. Okay, and here, this little sound emitting oscillator now is moving to the right. You can see that what we said in the previous slide is that as that source moves to the right, okay, the region in front of the source, it is in a sense catching up to the waves that it has just emitted. So the wave fronts are getting crowded, okay, in the region in front of the source, and in the region behind the source is moving away from the waves that it emits, okay, causing the wave fronts to get more diffuse, more spread out. So you can see here, when we compare the wavelength for the source at rest to the source in motion, okay, first of all, for this region, when the source is moving away from the observer, notice the increase in wavelength here, okay, that the wavelength is bigger, okay, when the source is moving away from the observer. And if a wave is traveling in a medium, an isotropic medium, where the speed is constant, we have this inverse relationship between wavelength and frequency. So if the wavelength gets bigger, the frequency must decrease. Okay, and if this happens to be a sound wave, that is why when the sound source is moving away from the observer, okay, there is a lowering of the frequency, a lowering of the pitch of the sound. Likewise, when we look at this region in front of the sound source, as the source moves towards the observer, we see that the source of sound is in a sense catching up to the waves it has just emitted. This causes the wave fronts to get crowded in the region in front. And you can see here very clearly that this causes the wavelength to decrease, okay, compared to the wavelength when the source was at rest. And like we said, for wave traveling in a medium at a constant speed, if the wavelength goes down, okay, the wave frequency must increase. So if this is a sound wave, this would explain why when the source of sound moves towards the observer, okay, why the pitch or the frequency of the sound would increase. So hopefully you see qualitatively, okay, why the frequency will change when the source is either moving towards or away from the observer. What we now want to look is we want to come up with a quantitative description of this frequency shift, okay, and we're looking at a case here where the source moves but the observer does not, so the observer is stationary. In a few slides, we'll also look at the case where the source is at rest, but the observer moves. Remember, when we defined the Doppler effect, we said it was a phenomenon whereby the frequency changes because of the relative motion, okay, between the source of the waves and the observer. So we really have both possibilities. The source can move, or the observer can move, or both can move at the same time. So let's start by considering a stationary source. That's what I'm showing you in this picture here. So the little red circle, it represents our oscillator, which is emitting waves. Notice the source is at rest. So what we can say is that these spherical waves travel outwards at a constant speed. So right at the initial time, this crest right here, well, I'm not showing you the entire crest, but this represents a wave crest that is emitted, okay, right at the start of the problem. I'll say T naught. Okay, this crest right here, this is a crest that has been emitted, okay, one period later. Remember, the distance between any two wave crests is the wavelength. The time between any two wave crests is the period of the wave. So, okay, you can see the wavelength, okay, described in the diagram here. Now, the distance between any two wave crests is a wavelength. I'm showing you that in the diagram. We said the time between wave crest emissions is what we call the period. Okay, now the distance the wave crest travels in a time equal to one period is what we call the wavelength. Okay, and remember this wave crest that I'm showing you here, okay, had to travel a distance equal to the wavelength in a time equal to the period. It travels that distance at a certain speed. What is that speed? It's the speed of the wave in the medium. So we can say the distance the wave crest travels in a time equal to 1 period, okay, is equal to v, which is the speed of the wave in the medium times time, right? Distance equals speed times time. So what we now want to look at is, okay, that's when the source is at rest. What happens when the source is now moving to the right? Okay, for the source that is moving towards the observer, okay, what can we say there? So here you see our source, this is now moving at a speed v sub s. Be careful, okay? The speed of the source and the speed of the wave are two very different speeds. Okay, so you see that as the source moves to the right, okay, and it emits a new wavefront, okay, you can see that that new wavefront is a little bit closer to the wavefront that was emitted 1 period before that. Okay, because the source is in motion, it is catching up to the wave it has just emitted. So this is what we'll call lambda prime. This is the new wavelength, okay, because of the motion of the source, as opposed to our original wavelength where the source is at rest. So we want to come up with an expression for lambda prime. So the distance the wave crest travels in a time equal to 1 period, okay, like we said, is simply the speed of the wave times the period. Okay, but now we've got to look at the distance the source travels. Okay, that's really this distance right here. Okay, notice that when the source was at rest, okay, here it is. But because the source is moving to the right, after 1 period, it is now a distance here, okay, equal to the source speed times the period. That's what this distance is. So we can say that the source travels a distance v sub s for speed of the source times a period, okay, in a time equal to 1 period. You can now see that this new wavelength, lambda prime, is really equal to the original wavelength lambda minus the distance that the source has traveled in that time, right? So the new wavelength, the smaller wavelength, the reduced wavelength, is equal to the original wavelength minus the distance that the source has moved, okay, between those wave crest emissions. So we can write here, just making the substitution. Remember, lambda, we said, was just equal to the wave speed times the period, so we'll plug that in right here. Okay, and once we have this expression for our new wavelength, we can get an expression for our new Doppler frequency f prime. So from our wave equation, the speed of the wave is constant in the medium, v, okay, but the wavelength and the frequency change. That's why we represent them as lambda prime and f prime. Solving for f prime equals v over lambda prime, and we will substitute in our expression for lambda prime. Okay, here vt minus v sub st, okay, which you see in our denominator down here. We'll factor out the period and recall that 1 over the period, the reciprocal of the period, is just the frequency. So at the end of the day, this is a quantitative expression for the frequency shift that occurs when the source is moving towards the observer. Notice that there are two speeds here. V represents the speed of the wave in the medium. V sub s represents the speed of the source in the medium. Notice that if V sub s is 0, that is if the source is at rest, okay, then you find out that f prime is exactly equal to f, right? If the source is not moving, we just get Vf over V, or just f. All right, so we have an expression for the Doppler frequency, okay, when the wave source moves towards the observer. Let's now take a look at coming up with this expression for when the source of the wave is moving away from the observer. So when we look at our diagram here, okay, we see that in this case, if the source of the sound is this moving car, as it's moving to the right, let's now take a look at the observer over here to the left. And you can kind of nicely see with this illustration that the distance between any two wave crests, this is a crest and this is another crest, is just equal to a wavelength. And you can see that the wavelength is certainly bigger there than it is when the source is moving towards the observer in this region over here. So on the previous slide we said that the new wavelength when the source was moving towards the observer, okay, was the original wavelength minus the distance that the wave source moved in a time equal to 1 period. But now, since we're looking at this region, we'll say the new wavelength is equal to the original wavelength plus the distance that the source has moved in a time equal to 1 period, in the time between emitting two waves. So the only difference here is we're replacing the minus sign with a plus sign. And from here, the calculations are pretty much identical. We have an expression for the new wavelength. The new frequency comes from the wave equation. Okay, and solving for frequency, okay, the wave speed being constant, we'll substitute in our expression for lambda prime. Okay, and remember the original wavelength lambda is just the speed, okay, the wave speed times, okay, the time it takes for a wave to travel a distance of one wavelength, which is the period. Okay, so lambda is just wave speed times period. And if we want to factor out, okay, a t from the denominator, we can do that and then write this in terms of frequency rather than period, recognizing that 1 over the period is simply the frequency. So here is an expression for the Doppler frequency shift when, okay, the source of the wave is moving away from the observer. All right, so we've looked at the case where the observer was at rest, but the source of the wave moved towards or away from the observer. And we have an expression for the changed frequency, the Doppler frequency, when that happens. What we now want to look at, okay, since we must look at the relative motion of source and observer, we're now going to look at the case where the observer is in motion, but the source of the wave is at rest. Let's compare the two situations and note some of the differences between the two. So the case we looked at on the previous slide, okay, moving source, stationary observer, and these, I'll just reproduce these pictures here. You can see that the wavelength changes, okay, when the wave source moves, okay, it catches up to the waves it emits in front of it and is moving away from the waves behind it. So clearly the wavelength changes, but the wave speed does not. Okay, the wave speed with respect to the observer does not change at all. So that remains constant. And our wave equation, v equals lambda prime f prime, tells us that the reason the frequency changes in this case is because the wavelength changes. Okay, but let's now take a look at a different scenario. So what I'm showing you here, this is the classic cartoon strip Calvin and Hobbes. Here you see Calvin's father yelling at him. But so the source of sound would be Calvin's father's voice. Notice that the sound source is at rest. It's not in motion, but rather the observer, that is Calvin, is moving, okay, relative to the source. So the observer Calvin is moving towards a stationary source. So in this case here, you can see in our wavefront diagram that since the source of sound is at rest, I should say the source of any wave is at rest, then the wavelength doesn't change, right? The wavelength anywhere you look is, identical to this situation here. The distance between wave crests will be the same distance, the same wavelength, regardless of where you observe that sound wave. So the wavelength remains constant. But here's the part that's different. The wave speed with respect to the observer. Okay, think about it. If there is a wave traveling from Calvin's father's voice throat to the right, okay, if Calvin is moving to the left, Calvin is moving towards the source that is emitting the sound. So the speed of the wave relative to Calvin will now be greater. And likewise, you could reason that if Calvin was running away from his father, okay, that he would say that the speed of the wave relative to him would now be smaller. So when we look at the wave equation here, notice that once again we get a change in frequency, okay, when our uh, observer is in motion, but for a very different reason, right? Because it's not because the wavelength changes, it's because the wave speed relative to the observer changes. So now that we've seen what happens to the wave speed relative to the observer, okay, let's now derive this expression for the frequency change, okay, for a moving observer stationary source. We'll start with a case where the observer moves towards the source of the wave. And like we said here, okay, v prime, that new wave speed relative to the observer, okay, would be equal to the wave speed when the observer's at rest, v, plus the speed of the observer, okay, towards the wave. So the wave speed relative to the observer would be greater than the wave speed, okay, where the observer's at rest. So v naught, speed of the observer, and v, the speed of the wave in the medium. So the new frequency, remember on the last slide we said the wave equation looks like this. The new frequency happens because, okay, there is a change in the wave speed relative to the observer here, but not because the wavelength changes. So when we substitute this new wave speed in, keeping the wavelength the same, okay, and we will substitute in the wave equation v equals lambda f. Okay, lambda therefore is equal to wave speed divided by frequency. When we make that substitution, okay, we can write our equation like this, that f prime equals, okay, v naught plus v divided by v over f, okay, and we will ultimately write it as such. Okay, so the new frequency is equal to the speed of the observer plus the speed of the wave in the medium, okay, divided by the speed of the wave in the medium times that original frequency. All right, so let's very quickly, okay, now that we have an expression for, okay, the Doppler frequency when the observer moves towards the wave source, okay, let's look at the last case where we have a stationary source, okay, that in this case, Calvin's father yelling, his voice, and a moving observer, in this case Calvin, where now our observer is moving away from the source. So all we're really going to do is be changing some signs in this slide. So the speed of the waves with respect to the observer now, v prime, is going to be the speed of the wave in the medium, okay, minus the speed of the observer. So v is simply the wave speed in the medium, okay, and we have to subtract the speed of the observer as Calvin moves away, okay, from the source of the sound. And we said that the new frequency, f prime, happens because not the wavelength changes, but the wave speed relative to the observer, v prime, changes. So we'll substitute in, okay, this expression right here. And we will then use our wave equation, okay, to write wavelength lambda in terms of v and f. Okay, and when we do, when we make that substitution, lambda equals v over f, okay, we find out that this new frequency is equal to, okay, the wave speed in the medium minus the speed of the observer divided by the wave speed in the medium times, okay, the original frequency of the wave. Now, in the previous 5 slides, we have derived 4 equations that we can use to calculate the Doppler frequency, that is the change in frequency, when either the source of sound is in motion relative to the observer, or the observer is in motion relative to the source of sound, or both. What we're now going to do is look at a simplified formula that will allow us to express all of these 4 equations, these 4 possibilities for the relative motion of the source of the wave and the observer of the wave. Okay, but we can put it into one nice compact little equation, and here it is. Now, you'll notice here that there really are 4 equations in this little compact statement because we have, okay, these choice of signs, as you'll see. Okay, the numerator, this could be a plus sign or a minus sign, and in the denominator, it could be a minus sign or a plus sign. So how do you know when to use each of these signs? Well, as we'll see, we will use the upper signs if the source and or observer are moving towards each other, because that will cause a frequency increase. So notice here that if we use the upper signs, using a plus sign in the numerator means we're adding these speeds, we're making the numerator bigger, okay, giving a higher frequency. And if we use the upper sign in the denominator, it's a minus sign. So when we actually subtract these 2 speeds, we make the denominator smaller rather than bigger, which will make the frequency bigger. And the other possibility, of course, is to use a lower set of signs, and in so doing, we would do that if the source and or observer are moving away from each other. Using the lower set of signs here causes the frequency to go down. Notice here, if I subtract the 2 speeds in the numerator, it makes the numerator smaller, whereas if I add, numerator smaller and frequency smaller, whereas if I add the 2 speeds in the denominator, it makes the denominator bigger, and therefore the observed frequency smaller. Now, we're going to gain some practice applying this formula in different scenarios, but here is my hint, my strong suggestion for how to go about using this formula in solving problems involving the Doppler effect. Instead of memorizing the signs for a given scenario, because there's lots of scenarios, ask yourself whether the situation in question, that is, the situation you're confronted with in your problem, will cause an increase or a decrease in the observed frequency for both the source and the observer. You can then choose the signs that will allow for the required increase or decrease in frequency. This means ultimately there's going to be a lot less memorization, and we'll take a look in the next few slides, okay, at how to apply this equation. All right, so let's take a look at this first of 4 sample problems. In this problem, we're told that as an ambulance travels east down Briggsmore at a speed of 30 meters per second, its siren emits sound at a frequency of 400 hertz. So it is always a good idea to draw a diagram showing, okay, if you have all of these possibilities, showing the source of sound and its velocity vector, okay, as well as the observer in the problem. And if the observer is in motion, you want to show the velocity vector for the observer as well. So do that for any problem, okay, to set it up. We're then asked in, part 1 of the problem, what frequency is heard by a person in a car traveling west? Okay, notice we have a car traveling west, ambulance traveling east. Car is traveling west at 25 meters per second as the car approaches the ambulance. Okay, so like I said in the previous slide, this is the approach you want to take. You want to ask yourself, does the motion of the observer cause a frequency increase? Does the motion of the source of the sound cause a frequency increase or decrease? Okay, then you'll know which signs to apply. Note here that if we look at the source of the sound the source of the sound is moving towards the observer, that should cause a frequency increase. Notice when we look at the observer is moving towards the wave source, that too should cause a frequency increase. So here we're going to use, okay, the upper signs here. So notice that it's the speed of the observer in the numerator, and we said that the motion of the observer, okay, the motion of the car towards the source of sound would cause an increase in frequency, so we're going to use a plus here. And we said that the source of sound, which that expression is in the denominator, the source of sound is moving towards the observer. That too should cause the frequency increase. So we're going to make the denominator smaller and use the minus sign. So once you figure that out, the rest is just plug and chug. Okay, and we have to make sure that we've got the numbers right. So remember, v, that is the speed of the wave in the medium, which for the sound wave is, for sound wave in air at room temperature, is about 343 meters per second. The v sub o, that is the speed of the observer. Okay, that's the guy in the car over here traveling at 25 meters per second. And notice that these are speeds, not velocities. Okay, the source of the sound is the siren on the ambulance, and that siren is moving at 30 meters per second. So we plug in those numbers. The original frequency of that siren, okay, as it is being emitted, is 400 hertz. The only difficult part here is choosing the correct sign. So we did that. Okay, we choose the signs that make the frequency increase for both sound source and sound observer, and when we do the number crunching, we get this value of 470 hertz. Always check, okay, the original frequency of the siren is 400 hertz, so yeah, we would expect that as the observer is moving towards that source of sound that it should be a higher frequency, which it is. All right, so in part 2 of the problem, okay, notice that we still have our ambulance traveling 30 meters per second in an easterly direction, emitting a sound from the siren at a frequency of 400 hertz. But in part 2, we're asked what frequency is heard by the person in the car traveling at 25 meters per second as the car moves away from the ambulance. So basically, this is what happened in problem 1, but now the car is past the ambulance. Our approach is going to be exactly the same. Let's ask ourselves, does the motion of the source of sound cause a frequency increase? Does the motion of the observer of the sound cause a frequency increase or decrease? So here we can reason that the source of the sound is moving away from the observer. That should cause a frequency decrease. And in this case, the observer of the sound is moving away from the source. That also should cause a frequency decrease. So we have really a frequency decrease, okay, for both of these motions. So to do that, and I just want to point out here that when I look at this expression, it's the observer speed on top. So I'm asking myself, okay, in the numerator, does the motion of the observer, okay, as the car relative to the source cause the frequency to go up or down? So here the observer is moving away from the sound. That should cause a frequency to go down. Okay, so I'm going to choose a lower sign. In the denominator, this is where we deal with the speed of the source. So I look at the source and I say, the source of the sound is moving away from the observer. That too should cause a frequency to go down. To make the frequency go down, I need to choose the plus sign in the denominator to make the denominator bigger. Once I've identified the two signs, the rest is very straightforward. I plug in the speed of sound, the speed of the observer, the speed of the source, and the original frequency, do the number crunching, okay, try not to make a mistake, and here we have the Doppler frequency of 341 hertz. Notice that if the original frequency of the sound is 400 hertz, okay, as that car passes the ambulance, it will measure a frequency of 341 hertz, which is clearly less. Okay, so here we see a decrease in the frequency due to the Doppler effect. All right, so in part 3 of the problem, okay, same ambulance, okay, that we had in parts 1 and 2, but in this case, we're asked to find what frequency is heard by a person in a car that's traveling 40 meters per second as the car approaches the ambulance. So you'll notice here that the car is moving faster than the ambulance, so it is actually going to be approaching the ambulance, moving towards it. So that is going to dictate that we choose a certain signs, okay, for our expression here. And here we will note that the observer is moving towards the emitted waves, okay, that should cause a frequency increase, but that the source of the waves, that is a siren, is moving away from the observer. So for the speed of the source, okay, we need to make sure that the frequency decreases. So when we look at our expression here, this tells us what signs we're going to choose. Like we said, okay, the observer here is in the car, is moving towards the source of the sound, so the motion of the observer, okay, towards the sound source should cause an increase in frequency. We will choose the upper sign. But we look at the source of the sound, the ambulance is moving away from the observer, okay, so the motion of the source of sound should cause the frequency to go down. So here we have these two contradictory effects. And in order to make the frequency go down, we want to make the denominator bigger. We will choose the plus sign in the denominator. Once again, that's the hard part of this problem. The rest is just plugging in numbers. So we'll plug in, speed of sound, speed of the observer, speed of the source of sound, the frequency of the source of sound. Do the number crunching here, and you will find out we get a frequency of 411 hertz. So you'll notice here that it is slightly bigger than the original frequency of the siren. And here you can see that one of the effects, okay, that is the motion of the observer, causes a frequency to go up. But the motion of the source causes a frequency to go down. It looks like overall the observer's motion is the more important one, because overall it causes the frequency overall to go up very slightly. All right, so in this fourth part of the example, we still have the same ambulance traveling east at 30 meters per second with its siren blaring at 400 hertz. Okay, but in this follow-up problem to problem 3, we're now asked to find the frequency, okay, heard by a person in the car after the car passes the ambulance that it was approaching. So once again, okay, we ask ourselves, how does the motion of the source of sound and the observer of the sound, how would each of their motions cause the frequency to change in the problem? And here we can say that, okay, the observer in the car, okay, moves away from the source of sound, okay, so that should cause the frequency to go down, but okay, the source of the sound, the siren, is moving towards the observer, so that motion should make the frequency increase. So once again, we have these two somewhat canceling effects. And when we look at our expression here, okay, for this Doppler frequency here, once again, the observer, the speed of the observer is in the numerator, and we said that the observer is moving away from the sound source. We should expect a frequency decrease, so we will choose the negative sign to make the numerator smaller. And once again, when we look at the source of sound, the source of the sound is moving towards the observer. Okay, the source of sound is in the denominator. Sound source moves towards the observer. That makes the frequency go up. So we would want to choose the upper sign, the negative sign here, to make the denominator smaller. So with those choices, okay, the rest is very straightforward. So we're going to choose the negative sign in the numerator, negative sign in the denominator, plug in the other numbers, and you'll notice here that we end up with a Doppler frequency of 387 Hertz, which is actually less than the original frequency. So these two opposing factors, you can see here, okay, that the motion of the observer away from the sound wave had the bigger effect, okay, was more significant in causing that frequency decrease than the motion of the sound source towards the observer was in causing the frequency to go up. So look, folks, I just want to say here that when you are solving these problems, it is important that you get these signs right. And I'll be honest, I'm not going to give credit if you get the signs wrong in the problem, because I don't think that, you know, if you to understand the physics means you have to understand how to choose the correct signs to make the frequency change, okay, according to the motion of both source and observer. So tell yourself that, okay, that you know you can plug in all the numbers, but if you get those signs wrong, you're going to get very little credit, okay, in your solution. All right, so in the examples we've looked at thus far, we have talked about the Doppler effect for sound waves. But like we said, the Doppler effect is a wave phenomenon and applies to all waves. So let's take a look at a couple of important examples of how the Doppler effect is used with electromagnetic radiation, okay, with light. So qualitatively, we'll take a look at how weather forecasting uses radar. And you may have heard on one of our local radio stations, KCRA3, they always talk about live Doppler radar. Okay, and this live Doppler radar is used to not only locate a storm, but to determine the speed of a storm as well. So let's take a look. If you take your transmitter here and you send a source of radar waves, and we will learn later that these are electromagnetic waves in a fairly low frequency. They're in a frequency of the electromagnetic spectrum that is below, okay, the frequency of visible light, so in the radar region of the spectrum. So when you shoot these low frequency light waves, electromagnetic waves at the storm, okay, the waves are sent and are reflected off the storm, and just like the way a motion detector works in our lab, the amount of time it takes between sending the waves, okay, between transmitting the waves and receiving the waves is detected, and knowing the speed of the waves, you can then figure out the distance of the storm, okay, or the location of the storm in relation to the radar, okay, transmitter. So the first thing that the transmitter does is to figure out how far away the storm is. The Doppler effect has not been used yet, but now, okay, the frequency shift of the reflected radiation is detected by the detector, and from that new frequency, okay, the computer can go through the calculation that we looked at on the previous slide. If this storm is now moving either towards, okay, the source of the waves, that is the radar transmitter, or away from the radar transmitter, okay, we can then use that equation to determine the speed of the storm. Okay, as long as all those other quantities are known, you can then use the equation. As long as you know the original frequency and the new Doppler frequency and the speed of the waves in the medium, you can then find the speed of, okay, the let's say the observer here, okay, the storm, as well. Perhaps even more importantly, the Doppler effect was used by astronomers to discover something very important about our universe, okay, and that is the motion of our galaxies. This is one of the biggest discoveries in astronomy, okay, in the last century. So, astronomers discovered that light we see from distant galaxies is shifted towards the red end of the electromagnetic spectrum. Now, in this visualization here, you can kind of see, okay, that if we have a source of light, like let's say a star that is moving away from us, if we're over here to the left, look what happens. Okay, that light gets shifted to the red end of the spectrum. If you're observing a source of the waves, let's say a distant galaxy moving away from you. If you were over here on the other side and that galaxy is coming towards you, okay, you would expect to see light shifted to the blue end of the spectrum. Okay, and just making that observation is very important. And we'll quickly go through this qualitatively here. So which color of light, red or blue, has a longest wavelength? Well, it turns out that red light has a longer wavelength than blue light. How does the frequency of red light compare to the frequency of blue light? Well, you know this inverse relationship between wavelength and frequency. Okay, so basically longer wavelength, lower frequency. That means the frequency of red light is less than the frequency of blue light. So here's the crux. In thinking about these answers, along with the Doppler effect, what can you conclude about the movement of distant galaxies? If we see the light from distant galaxies shifted to the red end of the electromagnetic spectrum, that would suggest that distant galaxies are moving away from us. That is, the source of the light waves, those distant galaxies, have to be moving away from us, the observer, to cause the shift towards the red end of the spectrum. And okay, we can look at that with one more visual here. Okay, you'll see here it's pretty much the same idea, but if you're an observer over here and the galaxy is moving away from you, you're going to see red light when you look through your telescope. If you were an observer over here and you see this galaxy moving towards you, okay, you will see a shift in blue light when you look in your telescope. So the last topic that we will introduce in this unit on sound is that of shock waves and sonic booms. In this slide, we will review, okay, some of the physics that we learned for sound sources, okay, when they are at rest and when they are moving relative to an observer. So a lot of this will serve as a review. When the source of the sound is zero, okay, when the source is at rest, okay, then the sound source sends out a spherical wave where the wavelength will be constant, okay, regardless of the observer, okay, regardless of where the observer is located looking at this wave. This is the case where the source of the sound is not moving. And we said when the source of the sound is moving, now we expect to see a Doppler effect, okay, a Doppler shift in frequency. Let's look at the case where the source of sound is greater than zero. In other words, the sound source is not stationary, but where the source of the sound is moving at a speed that is less than the speed of sound in the medium. And this is what we looked at. So in this case here, we see the sound source is moving to the right, and if you're in the region to the right, so you see that sound source moving towards you, you see an increase in frequency of sound, whereas if you're in this region over here to the left of the sound source and you see the source moving away from you, you would see the characteristic Doppler decrease in frequency, okay, of the sound wave. What would happen, however, if the source that is emitting the sound wave, okay, we're traveling so fast that it were actually traveling exactly at the speed of sound itself? Well, imagine what that wavefront diagram would look like. Okay, it would look like this. The source of sound emits a wave, okay, and that wave is traveling at a speed, the speed of sound in the medium, but so is the source of sound. It's also traveling at the same speed. So you see here how the sound source, okay, is always, okay, right, it is always right at the wavefront that it has just emitted. All right, so now we look at the case where we get the sonic boom. What happens when the source of sound exceeds the speed of sound? That means the sound source is traveling faster than the speed of sound. Well, if you take a look at that wavefront diagram, okay, you can imagine what would happen when the source of sound actually outruns the wave speed, the waves it's creating. And you see here, you get this conical shock wave where you get a whole lot of overlapping wavefronts. And it is these overlapping wavefronts, as we'll see next week, that is a source of constructive interference where a lot of energy is being produced and released. So when we ask the question, when is a shock wave formed? Okay, when you look at this wavefront diagram with these overlapping wavefronts, the shock wave occurs when the wave source outruns the wave it produces. In other words, when the wave source, okay, is traveling faster than the speed of the wave in the medium. Okay, so when an airplane, for example, can travel faster than the speed at which sound travels in the medium, you will get a sonic boom. And we'll take a look here. You see observer 1, observer 2. Okay, the wavefronts have to actually, hit those observers before the sonic boom is heard. So in terms of wave interference, what is happening when a shock wave is formed? Well, like I said, we haven't looked at this phenomena yet, but we will next week. Whenever you have wave fronts overlap, that represents a condition we call constructive interference, which means you produce a very large amplitude wave. Remember, the amplitude of the wave is a measure of the energy that the wave transports. So when a large number of wave fronts overlap, creating a very large amplitude wave, that wave has a lot of energy, and that is what we call a shock wave. Breaking the sound barrier. Maybe this is a phenomenon you've heard about. There is extra thrust of the plane that is needed to break through the sound waves in front of it. Okay, less energy is actually required at supersonic speeds. So you recall in the last slide, when the wave source is traveling exactly at the speed of sound, okay, so that the source has all of those wave fronts right in front of it, okay, that requires an extra burst of energy to break through. But once it does, then motion becomes very efficient. And if you look at one of the advantages of supersonic speeds, like what the Concorde did while it was flying for the decade that it was, is it could fly very efficiently. This was a plane that was designed to cross the Atlantic Ocean in very short times. Flights were very expensive, of course, didn't hold a lot of people, but it could travel at supersonic speeds, and it could get really good gas mileage. Once the sound barrier was exceeded, okay, the motion was quite efficient, and less energy was required to make the plane move. Of course, sonic waves, sonic booms are a source of noise pollution. So, typically this supersonic travel is not allowed in areas where people live because it's unpleasant and can be damaging to buildings and eardrums. But over the Atlantic, I guess the same, international restrictions didn't apply as you're flying over international waters. So the sonic boom observed on the ground when the conical shock wave passes the observer. You can see here this conical shock wave. Notice here that really there are, well, let me put this up here. Why will most observers hear two sonic booms? Because if you look at the picture here, there is a shock wave formed on the front of the plane, right? You see this conical shock wave, as well as the rear of the plane. So very often, if you're observing this, you will hear two sonic booms in very close succession to one another. The first one when the shock wave from the front of the wave passes you. The second one when the shock wave from the rear of the plane passes you. So you'll notice here with these observers on the ground that, okay, the observer over here on the far left has heard both sonic booms. The observer in the middle, okay, has simply heard the sonic boom from the back of the plane, but the sonic boom from the front of the plane, that shock wave hasn't, okay, entered that person's zone yet, whereas this person here on the right has not heard anything yet, okay, because, you know, that shock wave, those wave fronts have not intersected that person's space.